discuss 17th group elements. These 17th group elements are also known as halogens. The word halos stands for sea salt forming, because these elements are found in oceans and seas as their salts, like sodium chloride, sodium bromide, potassium iodide, potassium fluoride, etc. So because of their salt forming nature present in the sea and oceans, these 17 group elements are collectively known as halogens. So starting with this, group 17. These elements are known as halogens. So means sea salt forming. So the elements of this group 17, these are fluorine, chlorine, bromine, iodine, and the last one is astatine. This last element, astatine, this is radioactive and all these elements are found in sea as the salts. So because of this, these are known as halogens. These group 17 elements, they have general electronic configuration, of the valency cell, that is NH2 NP5. This quantum number n, that is the valency cell, if you look at this electronic configuration, we have 2 electrons in s orbital and 5 electrons in p orbital. So this p5, we have 3 orbitals in p, px, py and pz, and there are 5 electrons. So look at this. This electron is paired up, this electron is also paired up, and we have this electron, that is unpaired electron. These unpaired electron may be in px, maybe in py, or maybe in pz, and spin quantum number may be plus half, minus half. So this is the general electronic configuration of this group 17. So if you look at this, NH2 and NP5, N being the highest occupied shell number, the number of electrons present in the valency cell. So look at this, valency cell contains 7 electrons. Total number of electrons in the valency cell is 7, and this contains 1 unpaired electron. Out of these 7 electrons, 2 is present in s orbital and remaining 5 electron is present in p orbital. So s orbital is completely occupied, means both the electrons are paired up, whereas in case of p5, 4 electrons are paired up and the last 5th electron is unpaired electron. The group number is 17. So group number, that is 10, plus number of electrons in the valency cell, that is 7. So we have 17th group. Period number is equals to the valency cell, the value of n of valency cell, highest occupied shell number, that represents the period number. So once we know this, we can easily identify the location of this group 17 elements. So this is general electronic configuration. Now coming to some of these properties. We have these elements: fluorine, chlorine, bromine, iodine, and the last one is astatine, which being a radioactive. So this term asterisk mark represents the radioactive elements. So first of all, we'll discuss size or radius of these group 17 elements. So moving from top to bottom, due to increase in extra shell or due to addition of extra cell, the size of these group 17 elements shows a gradual increase from fluorine to astatine. So both the atomic radius and the ionic radius, so size of atom or the size of ions, both increases from fluorine to astatine, and these increase in size due to addition of extra shell. That is normal as expected. Then next is atomicity. All these elements of group 17, the atomicity is 2. That is, this exists as fluorine F2, Cl2, Br2, I2. Now let's skip this part. This being radioactive, most of the chemistry is not known, so we will focus on the chemistry of this fluorine, chlorine, bromine and iodine. So if you look at this, in elemental state, the atomicity is 2. All these elements exist as diatomic molecule, and this atomicity 2 means these being non-metals, the bond between X2, so we have this X2. While we have discussed electronic configuration, we said there is one pair of one electron that is unpaired left in p orbital. So these overlaps to form sigma bond. So we have X, that is sigma bond. And after formation of this sigma bond, each halogen is having 3 lone pairs of electron on each halogen. This represents lone pair electrons. So this is the atomicity of these elements. Then coming to physical state of these elements. Fluorine and chlorine both exist as gas at room temperature. Bromine exists as a liquid at room temperature. Mind it, this is the only non-metal that exists at liquid state. Bromine is the only non-metal that exists as liquid at room temperature. Iodine exists at solid state. So if you look at this, moving from fluorine to iodine, the physical state changes from gas to liquid, and liquid to solid state. Now, once we know the physical state, there is gradual changes from gases to liquid to solid state. While we considering this, the melting point and boiling point of these elements, melting point and the boiling point of these elements again increases down the groove. Now we can easily explain this gradation or the increase in melting point and boiling point down the groove from fluorine to iodine based on their size or intermolecular attractive force. Now look at this. This fluorine, chlorine, bromine or iodine or X2. Now we have this X2 and this X2. The intermolecular attractive force between these X2 molecule, that is weak van der Waals force. So because of this being weak van der Waals force in the lattice structure in between two adjacent halogen molecules, the molecular attractive force is weak van der Waals force. Because of this being weak van der Waals force, these halogens are volatile. So this represents volatile nature. All these halogens are volatile. So the reason being because of weak intermolecular van der Waals force of attraction between the adjacent molecules. Now look at this. Moving from fluorine to iodine, the size of molecule increases. As the size of molecule increases, the attractive force between the molecule also increases. As the attractive force between the molecule increases, the melting point or the boiling point increases. So simply saying, fluorine to chlorine, size increases. As the size increases, intermolecular attractive force between the halogen molecule also increases. Now moving from chlorine to bromine, again size increases, and from bromine to iodine, again the size increases. So due to increase in size, moving from fluorine to iodine, the intermolecular attractive force also increases. As the intermolecular attractive force increases, energy required to break this bond also increases. So as the energy required to break this intermolecular attractive force increases, the melting point of these elements also increases. Similarly, we can also say the boiling point also increases. So we can say this is due to increase in intermolecular attractive force, and this increase in intermolecular attractive force, this is because of increase in size from fluorine to chlorine. So this is variation in melting point and the boiling point. Now after this, let's discuss some other points also. Volume and density. Both volume and density of these elements also increases down the groove. So density as well as the volume of these elements increases down the groove. Now you may ask, if volume is increased, then the density should have been decreased, because density is defined as mass per unit volume. Now moving down the groove, volume of elements increases, but the density also increases. So that means density is a ratio of mass per unit volume. As the volume decreases, density should decrease, but along with increase in volume, there is also increase in mass. So moving down the groove, mass as well as volume increases, but the increase in mass dominates over the increase in volume. is the increase in mass is greater than the increase in volume, the atomic density also increases down the groove. Then color of these elements, all these elements shows different color. So let me give you the colors. Fluorine, light yellow, chlorine, greenish yellow, bromine, reddish brown, iodine, violet. So there is a distinct color of these halogens. Fluorine, light yellow, chlorine, greenish yellow, bromine, reddish brown, iodine, violet. Now look at this. Why this element shows color? Now in previous lectures or in earlier classes we have discussed the color of transition elements and their complex also. So color basically arises, these elements absorb energy from the visible region and that energy is used to excite the electrons present in the outermost shell. So electron is excited by use of energy from visible region and electron is excited. Now excited state being less stable, electron comes back to the ground state. So during this de-excitation process, energy is released and this released energy falls in visible spectrum and color appears. So if you look at this, fluorine, light yellow, yellow, greenish yellow, reddish brown or violet. If you look at this, intensity of color increases, intensity of color increases. That means fluorine being the smallest in size, the attractive force between the Valency shell and the nucleus must be the highest. As the attractive force is more, so these electrons to excite will require higher energy. If energy is more, energy is required, means shorter wavelength should be absorbed. So in terms of absorption, moving from this fluorine to iodine, wavelength of absorbed light, so wavelength of absorbed light increases. That means fluorine being the smallest requires maximum energy to excite the electrons from ground state to the excited state. So if energy is maximum, energy of excitation is maximum in case of fluorine, so the wavelength of absorbed light should be the minimum. Iodine being the largest in size, the attractive force between the valence electron and the nucleus being the least, so least energy is required to excite electron. Now energy required is least, so therefore the wavelength should be the maximum. So look at this, wavelength of absorbed light increases from fluorine to iodine, the wavelength increases. So if you look at this, in visible region that is changed from VQ, violet, to red. To absorb light, frequency decreases or wavelength increases. So this is the color of these halogens, why this color appears and what is the change in wavelength of absorbed light or the frequency of light. After this, we'll explain the bond length. Bond length of XX, bond distance of XX. Now look at this. Fluorine being the smallest, the bond distance between two fluorine atoms in fluorine elemental state should be the minimum. As the size of halogen increases, the bond length of XX bond also increases. So this is due to simply increase in size from fluorine to iodine. The bond distance of XX bond increases from fluorine to iodine. That means FF bond is the shortest, II bond is the longest. Now once we have this bond length, now let's discuss bond dissociation energy. Bond dissociation energy. Bond dissociation energy. That means enthalpy of dissociation of XX bond. Now we have just seen it F2 bond being the shortest, I2 bond being the largest. Now if the bond length is less, bond strength is more. So if the bond length increases from fluorine to iodine, the bond dissociation energy must decrease from in fluorine to iodine. But look at this, the bond dissociation energy order of these halogen appears as Cl2 is greater than Br2, which is greater than F2 than I2. Now look at this, look very carefully. Bond length says F2 is the shortest bond, I2 is the longest bond. So there is a gradual increase in bond length from fluorine to iodine. If fluorine-fluorine bond is the shortest, then fluorine-fluorine bond should have been the strongest bond. If the fluorine-fluorine bond अगर strongest है तो energy required to dissociate the fluorine-fluorine bond should be the highest होना चाहिए. But look at this, यहाँ पे देखिए. Now we have to explain this. Why the bond dissociation energy of fluorine is less than bromine? होना चाहिए था बहुत ज्यादा, लेकिन ब्रोमीन से भी कम हुआ. अब ये क्यों कम हुआ? We have to explain. So the reason being is, if you look at this, fluorine, so we have this. No doubt fluorine is the smallest, so bond distance between fluorine and fluorine is the shortest. As I told you earlier, after formation of this sigma bond, each fluorine के पास 3 lone pairs of electron है, and these lone pair, ये lone pair electron, और ये lone pair electron किसमें present है? 2p orbital, because fluorine is in second shell, second period. Now if you look at this, size of 2p अगर very small है, और उस small 2p में we have these electrons. अब take this 2 fluorine है, small in size, and each fluorine के 2p orbitals में 3 lone pairs of electrons हैं. अब ये दोनों very close to each other हैं. So if these fluorines are very close to each other, there is a strong repulsion between non-bonded electrons present in small 2p orbital. So because of this enormous repulsion between these non-bonded electrons present in 2p orbital, the bond dissociation energy of fluorine is the lowest, but still this is less than that of bromine. So these lone pair undergoes strong repulsion. So these strong repulsion between non-bonded electrons of 2p orbital is responsible for the low bond dissociation energy of fluorine. So since the size of fluorine being the smallest, the distance between the lone pair is the closest, so repulsion is the maximum. So because of this strong or maximum repulsion between non-bonded electrons present in 2p orbital, the bond dissociation energy of bromine is less than that of, fluorine is less than that of bromine. Now as the size increases, distance between the halogens also increases. As the distance increases, distance between non-bonded electrons also increases. As the distance increases, repulsive force becomes less. So here look at this. Distance between fluorine shortest है, तो bond should have been strongest, तो bond dissociation energy should have been the highest, but यहाँ पे कुछ और effect है, bond shortest no doubt. Along with this, the distance between the non-bonded lone pair electron is also least. Because of this, there is a strong repulsive force acting between this non-bonded lone pair electron. So here look at this. The low this bond dissociation energy of fluorine is attributed to strong repulsive force between non-bonded electrons present in these 2p orbitals. So this repulsive force dominates over this shorter bond distance. As a result, the bond dissociation energy of halogen follows this order. So please, bond length normally increases from fluorine to iodine, but in case of bond dissociation energy, fluorine bond dissociation energy is the less than bromine. So the reason being the strong repulsive force between non-bonded electrons present in 2p orbitals of fluorine. Due to its small size, this repulsive force dominates over the short or smallest bond distance present between two fluorine atoms in fluorine molecule. So this is the bond dissociation energy of halogens. Now coming to next, ionization energy. Now these elements, fluorine, chlorine, bromine, iodine, these are non-metals. So as these are non-metals, the ionization energy of these non-metals are generally very high. And if you look at this, these elements have 7 electrons in the valence shell. So this requires 1 more electrons to add a noble gas configuration. Now as these elements require more electrons to complete octets, the ionization energies of these elements are very high. But still, moving down the groove, size increases. As the size increases, the ionization energy of these elements also decreases down the groove. So moving from this, ionization energy increases. The reason being due to increase in size from fluorine to iodine. Now, as the ionization energies are, these are very high. The reason being due to the presence of seven electrons in valency cell. So after acquiring one electron, this will achieve noble gas configuration, hence their ionization energies are very high. So since the ionization energy being very high, these are non-metals, but so look at this, moving from fluorine to iodine, ionization energy decreases. And so as the ionization energy decreases, the metallic character also increases. Though these are non-metals, but their metallic character increases down the group, so metallic character increases down the group, means these iodine shows a slight metallic character. So metallic means a metallic lustrous shining property. Iodine shows lustrous or shining property which is attributed to the metals. So these are non-metals. Because of this, they have strong or high ionization energy. The reason being due to the presence of 7 electrons in the valence shell. They still requires 1 more electrons to complete octet. So they are having very high ionization energy. But due to increase in size from fluorine to iodine, ionization energy decreases. As the ionization energy decreases, metallic character increases. So iodine shows slight metallic character like shining property, and these also show some plus oxidation state, also shows positive oxidation states in compounds like ICl, ICN, etc. So because of this is only possible because of this being slightly metallic in character due to low ionization energy along these elements. These elements, electronegativity, we know halogens are the most electronegative elements of all the elements present in the periodic table. So moving from left to right in a period, these halogens has got the highest electronegativity. So the electronegativity of halogens are the highest in a period. But moving from fluorine to iodine, the electronegativity decreases. This is due to increase in size. So as the size increases, tendency to withdraw electron density towards itself decreases. The reason being, due to increase in size, the attractive force between the valency shell electron and the nucleus is decreased. As the attractive force decreases, tendency to withdraw electron density decreases. So fluorine being the smallest, the distance between the nucleus and the valency shell electron is the shortest. So this has got strong attractive force. So moving down the group, electronegativity decreases. These fluorine, so I'm talking about fluorine, the most electronegative element. The most electronegative element of all the elements present in the periodic table. So no doubt periodic table में कितने भी elements present है, more than 180 elements are present as of now. तो उनमें से सबसे ज्यादा electronegative element is fluorine. Electronegativity scale, no doubt this electronegativity is just a theoretical concept which doesn't have any practical experimental justification. So Pauling says this fluorine, the electronegativity of fluorine is attributed, given as an arbitrarily assigned as a value of 4. So the highest value of electronegativity is the 4. So fluorine is assigned 4 value. So the rest of the elements का electronegativity 4 से कम होगा. So down the group electronegativity decreases because of increase in size, tendency to withdraw electron density towards self decreases. So this is electron negativity. Now coming to electron gain enthalpy value. Electron gain enthalpy. These elements, if you look at these elements has got 7 electrons in the valency shell, so NH2, NP5, and these elements are strongly electronegative. They have a strong tendency to withdraw electron. So these acquires one more electron and is converted into halide ion. Halide ion. So 7 plus 1, so this acquires an electron. So we have Ns2 Np6. So we have octet complete. So since these elements has a strong tendency to acquire one more electrons to complete its octet, so that it acquires the configuration of next noble gas. Now, because of this, the electron gain enthalpy values of these elements are very large, and all these values, so delta H electron gain enthalpy of all these elements are large negative. That means large amount of energy is released when an electron is added to neutral isolated gaseous atom. This is defined as electron gain enthalpy. So when we compare electron gain enthalpy values in a period, halogens has got the largest value of electron gain enthalpy values. But while comparing this electron gain enthalpy values of these elements, the variation in electron gain enthalpy values, this is Cl is greater than fluorine, then we have bromine, then we have iodine. So again look at this abnormal values here. So moving from chlorine, bromine, iodine, we can easily explain. As the size increases, the attractive force between the added electron and the nucleus, because electron is to be added in valency shell, so distance between the valency shell and the nucleus increases. As the distance between the valency shell and the nucleus increases, the attractive force between the added electron and the nucleus decreases. As the attractive force decreases, amount of energy released also decreases. But look at this, fluorine being the smallest in size, the distance between the added electron and the nucleus should have been the least, so the attractive force should have been the more. So most largest value of electron gain enthalpy value should have been for fluorine, but again यहाँ पे abnormality है. So again these abnormal values or the electron gain enthalpy values of fluorine is less than that of chlorine है. तो इसका जो रीजन है, this is again attributed to small size of 2p orbital, because size of fluorine is less than size of chlorine, so the size of 2p orbital of fluorine is less than size of 3p orbital of chlorine. So due to this small size of 2p orbital, electron density is more, small size of 2p orbital, already we have 5 electron, so electron density is more. Because of this high electron density, the added electron strong repulsive force felt by the added electron. So again look at this abnormal values of this fluorine or anomalous property of fluorine. Due to small size of 2p orbital, electron density on 2p orbital is very high. So when we add extra electron, this small size 2p orbital, there is a strong repulsive force felt by the added electrons. Because of this repulsive force, the amount of energy released during this process is less. But moving from fluorine to chlorine, size of orbital increases, size of 3p is more than that of size of 2p. Because of larger size of 3p orbital, electron density is less. As the electron density is less, the added electron felt less repulsive force. So the electron gain enthalpy values of chlorine is always greater than fluorine. Now look at this. In previous groups also, the electron gain enthalpy values of third period elements is always greater than that of second period elements because of same region. So third period, second period, due to small size, electron density is more, so repulsive force is more, so electron gain enthalpy values is always less. So this is electron gain enthalpy values of these elements. So except for this abnormality between fluorine and chlorine, down the group electron gain enthalpy values decreases. So this is variation in electron gain enthalpy. Now coming to the reactivity of these elements. Reactivity of these elements. So moving from fluorine to iodine, the reactivity of halogens decreases. So fluorine is the most reactive. So look at this. Now we have to explain this reactivity sequence. Fluorine being the most reactive, iodine is the least reactive. Whenever we have reaction between fluorine and others, the reaction is highly exothermic and it becomes explosive in nature and it's very difficult to control the reaction also. Now we have two contrasting factors here. We have look at this fluorine fluorine bond and chlorine chlorine bond. So enthalpy of dissociation of chlorine is greater than fluorine. Electron gain enthalpy of again chlorine is greater than fluorine. Now if you look at this, electron gain enthalpy values of chlorine being greater than fluorine. So when we discuss the reactivity, because all these halogens reacts to give you halide ion, so therefore look at this electron gain enthalpy values of halogen, that is chlorine, greater than fluorine. So obviously look at this, the reactivity of chlorine should be greater than that of fluorine. But when we look at this electron in dissociation enthalpy of chlorine being greater than fluorine, the energy required to break fluorine bond is very less due to high repulsive force. So fluorine should have been more reactive. Now look at this, both are in opposite direction. Dissociation enthalpy says fluorine should be more reactive than fluorine because energy required to break fluorine is greater than energy required to break fluorine. But when we look at this electron gain enthalpy values, chlorine electron gain enthalpy value being greater than fluorine, so chlorine should have been more reactive than fluorine. So, but when we look at this reactivity is always maximum for fluorine than that of chlorine. The reason being the dissociation enthalpy of fluorine being less, this bond can be easily break. Second, due to fluorine being small in size, it forms very strong bond. So this reactivity of this depends on two factors. Enthalpy of dissociation. Enthalpy of dissociation is least for fluorine, so fluorine should be. Second, fluorine forms, this is, we have just due to strong repulsion. Fluorine, second, I told you, fluorine being the smallest forms the very strong bond. Now, why fluorine forms very strong bond? The formation of strong bond is attributed to two factors. First, due to small size. So, due to its small size, it forms strong bond. Means coordination high coordination number. Fluorine due to small size forms high coordination number compound. Means along a given center the more number of fluorine can be formed. As the number of bonds formed between fluorine increases, energy release also increases, bond becomes much stronger. Second, high lattice energy. So due to this high lattice energy of the bond formed between atom and the fluorine and high coordination number, these fluorine always form strong bond, and because of this strong bond formation, fluorine is more reactive. And if you look at this, fluorine एक ऐसा element है this can react with all the elements present in the periodic table except light noble gas like helium, neon, argon. इसको छोड़ के जितने भी एलिमेंट्स हैं ये फ्लोरीन के साथ बॉन्ड बना सकते हैं. तो हाई रिएक्टिविटी के दो कारण है. Dissociation energy of fluorine is the least because of strong repulsion between 2p electrons. Second, fluorine always forms a strong bond. तो strong bond किसकी वजह से? Due to high coordination number and high lattice energy. So this is the reactivity order. So don't get confused with this electron gain, enthalpy and dissociation energies. Okay, this is the reactivity order. Now these halogens shows very strong oxidizing property. So coming to the next, reduction potential and oxidizing property. Reduction potential and oxidizing property. Now these elements, fluorine, chlorine, bromine, iodine, all these elements of halogen, the reduction potential, that is E reduction, standard reduction potential, this is always positive. The reduction potential of these halogens is always positive. If the reduction potential is positive, this simply means these are strong oxidizing agent. So simply saying, all these elements are strong oxidizing agent. But if you look at this, moving from fluorine to iodine, this standard reduction potential down the group decreases. So the standard reduction potential of fluorine being the largest positive is the strongest oxidizing agent. As the positive value decreases, the oxidizing character of these elements decreases. So fluorine is the strongest oxidizing agent and iodine is the least oxidizing agent. Again, look at this. This oxidation or this oxidizing character or oxidation potential or this depends on the energy difference between the element in the standard state and the hydrated state. So look at this. This reduction potential or oxidizing property depends on energy difference between element in standard state and hydrated state. So this difference gives you the reduction potential, or we say this oxidizing character. Now this value depends on, look at this, let's take this iodine. Iodine is solid state. Now this is to be converted into I minus hydrated state. This energy difference. Now we have to find energy difference. Now first look at this. This iodine solid is to be converted into iodine gas. So we require energy of atomization. So this atomization is always positive. We will supply energy. Now after this is to be converted into atomic iodine. So we require energy known as enthalpy of dissociation. Again this is positive. Now this I is to be converted into I minus, that is electron gain enthalpy, which is positive. So this I minus gas is to be converted into hydrated state, and we say this is enthalpy of hydration, this is negative. So these energy sequence, these energies will decide the oxidizing character or oxidizing agent nature of these halogens. So when we look at this enthalpy will decide. When we look at this enthalpy, this enthalpy change is most negative for this fluorine and the least for iodine. So the enthalpy change being the most negative for fluorine has got the strongest oxidizing character, and the reduction potential of fluorine is having the highest positive value. So this is oxidizing character. That means fluorine means, in one way we can say, an halogen of low atomic number will always oxidize halide ion of higher atomic number. This statement is halogen of lower atomic number will oxidize halide ion of higher atomic number. Then let's look at this. Fluorine is the strongest oxidizing agent. I have told you the reason why fluorine is the strongest oxidizing agent. So summing up this, we can say this: fluorine can react with X minus when this gives you 2F minus plus X2. So fluorine is changing from 0 to -1, that is reduction, and X minus changing from -1 to 0, this is oxidation. So fluorine is oxidizing agent, is oxidize X minus to give you X2. So here this X could be Cl Bri. So look at this, fluorine oxidize chloride ion, bromide ion, or iodide ion. So now look at this, fluorine oxidize this halide ion, chloride ion plus X2, Here X will be bromine, iodine. So chlorine cannot oxidize fluoride ion. Chlorine can oxidize bromine as well as iodine. Similarly, look at this. Bromine will oxidize I minus to give you bromide ion and iodine. So this is halogen of lower atomic number oxidize halide ion of higher order. So look at this halogens. If you look at this, F2, Cl2, Br2, I2. When this is ethically oxidizing, this is converted into F minus, Cl minus, Br minus, I minus. So comparing oxidizing property. Fluorine, chlorine, bromine. When this halogen acts as an oxidizing agent, this halide ion acts as a reducing agent. So fluorine being the strongest oxidizing agent, F minus will be the least reducing agent. So the reducing character increases from F minus to Cl minus to Br minus to I minus. So halide ions are reducing agent, whereas halogens are oxidizing agent. So as a reducing agent, Hi is the strongest reducing agent, so I minus is the strongest. Look at this, I minus reduces bromine, I minus reduces chlorine, I minus reduces fluorine. So this I minus is the strongest reducing agent. Fluorine is the strongest oxidizing agent. So again I am telling you, this reduction potential or oxidizing character depends on energy difference between element in the standard state and hydrated state. So that energy difference being the most negative for fluorine and the least negative for halogen, that is iodine. So the fluorine has got the largest value of the reduction potential. So this is the strongest oxidizing agent. Now coming to oxidation states of these elements. Oxidation states. Oxidation states of these elements. Now we have discussed electronic configuration. Now these elements contain 7 electrons in the valency cell. So by acquiring one more electron, this acquires octet configuration, that is noble gas configuration. Now since these acquires noble gas configuration by acquiring one electron, so the most stable oxidation state or the most common oxidation state of all these elements is -1. Most common is -1. As I told you, why? Because by acquiring one more electron, it acquires noble gas configuration. Apart from this, look at this. Fluorine shows -1 only, but chlorine, bromine, iodine shows -1, +1, +3, +5 and +7. So fluorine shows -1 only because this is the most electronegative. So fluorine being the most electronegative shows only one oxidation state, that is -1. Whereas the rest of the elements shows -1, +1, +3, +5, +7. These higher elements showing positive oxidation state, this is not because of the complete removal of electrons from the p orbital or the s orbital. This is due to the presence of vacant d orbitals due to the presence of vacant d orbitals, electrons can be excited to d orbital. As the electron is excited to vacant d orbital, during hybridization, d orbital can also be involved. As a result, the oxidation state increases from +1, +3, +5 to +7. Whereas fluorine, being the smallest, most electronegative, does not have vacant d orbital, so electrons cannot be excited to d orbital. So fluorine shows only one oxidation state, absence of d orbital. So this is the oxidation states of these elements. The most common is -1 because by acquiring one electron, this acquires noble gas configuration. But fluorine shows only one oxidation state, that is -1, the reason being the most electronegative, and this doesn't have the orbital. Chlorine, bromine, iodine shows plus oxidation state. This is due to the presence of vacant d orbital and electron is excited to the d orbitals. Can be excited and d orbital can be involved in hybridization. So this is the positive oxidation state shown by this halogen. So this is the oxidation state. Now finally look at this solubility. If you look at this H2 molecule that is non-polar, in non-polar. Now this being in non-polar, these elements are less soluble in water, but these are more soluble in organic solvents. Less or poor soluble in water, but they are very much soluble in benzene, chloroform, carbon tetrachloride, carbon disulfide. These are non-polar solvents. But apart from this, look at this. Fluorine reacts with water. So this gives you oxygen and ozone. So fluorine not dissolved in water but reacts with water. When fluorine reacts with water, this gives you ozone as well as oxygen. If less quantity of water is used, this gives you oxygen. If more quantity of water is used, this gives you ozone. Chlorine and bromine reacts with water when this gives you HCl or HBr plus HOCl or HOBr. आयोडीन जब ये रिएक्ट करते हैं तो बनना चाहिए था HI plus HOI, but this reaction is not spontaneous in forward reaction, but this is spontaneous in reverse. So this is not the solubility, but how these elements react with water. So these are some of the properties that we have discussed. After this, we'll go to the chemical properties of some important compounds that we'll take up in next class.